Alright, let's solve this carefully from the beginning and pay attention to how each piece of information connects to the next. We have a right triangle PQR with the right angle at Q and a circle with center O inside the triangle. The side QR is tangent to the circle at point T. The hypotenuse PR passes through the circle and meets the circle at P and S. We are given that PQ is 4 units, PS is 4 units, and SR is 1 unit. Our goal is to find the radius of the circle. So, let's begin by looking at the hypotenuse PR. Since S lies between P and R, the entire length PR is simply PS plus SR. Therefore, PR equals 4 plus 1, which gives us 5 units. So we already know that the hypotenuse of our right triangle is 5 units. Now let's focus on the tangent and secant relationship. From point R, the segment RT touches the circle at exactly 1 point, T. So RT is a tangent segment. Meanwhile, the line from R through S and P passes through the circle, so RSP is a secant. The tangent-secant theorem tells us that the square of the tangent segment equals the external part of the secant multiplied by the entire secant. In this case, that means RT squared equals RS multiplied by RP. Notice that RS is 1 unit, and we already calculated that RP, which is the entire hypotenuse PR, is 5 units. So, let's substitute those values. RT squared equals 1 multiplied by 5. Therefore, RT squared equals 5. To undo the square, we take the positive square root because a length cannot be negative. So, RT equals square root of 5 units. Keep that result in mind. We'll use it in just a moment. Now let's move to the right triangle PQR. Since the angle at Q is 90 degrees, we can use the Pythagorean theorem. Remember, the Pythagorean theorem says that the square of one leg plus the square of the other leg equals the square of the hypotenuse. Here, the two legs are PQ and QR, while PR is the hypotenuse. So we can write QR squared plus PQ squared equals PR squared. We know that PQ is 4 and PR is 5, so substitute those values. We get QR squared plus 4 squared equals 5 squared. 4 squared is 16, and 5 squared is 25. So our equation becomes QR squared plus 16 equals 25. Now subtract 16 from both sides. The 16 on the left cancels, leaving QR squared equals 9. Taking the positive square root gives us QR equals 3 units. Excellent. So now we know that the entire bottom side QR has length 3, while the portion from R to T has length square root of 5. Therefore, the remaining segment, QT, must be the entire QR minus RT. So QT equals 3 minus square root of 5 units. This is an important little segment, so keep it in mind. Now, let's bring the circle back into the picture. We know that OT is a radius of the circle because O is the center and T is a point on the circle. So, OT equals our unknown radius, which we'll call R. Also, there is a very important property of tangent lines. The radius drawn to the point of tangency is always perpendicular to the tangent line. Since QR is tangent to the circle at T, OT is perpendicular to QR. Now, let's drop a perpendicular from O to the side PQ and let that perpendicular meet PQ at F. Since QR and PQ are perpendicular to each other, and OF is perpendicular to PQ, OFA is parallel to QR. At the same time, OT is perpendicular to QR, so OT is parallel to PQ. This creates a small rectangle, QFTO. And because opposite sides of a rectangle have equal lengths, QF equals OT, which means QF equals R. R, the radius. Likewise, OF equals QT. We already found QT, so F equals 3 minus square root of 5 units. Now look at the entire side PQ. We know PQ is 4 units, and QF is R units. Therefore, the remaining segment PF must be 4 minus R. So at this point, inside the larger triangle, we have a smaller right triangle PFO. Let's look at that triangle carefully. The angle at F is 90 degrees because OF was constructed perpendicular to PQ. The side PO connects the point P on the circle to the center O, so PO is a radius. Therefore, PO also has length R. The other two sides are PF, which is 4 minus R, and OF, which is 3 minus square root of 5. Now we can apply the Pythagorean theorem one more time. The two legs squared add up to the hypotenuse squared. Therefore, we can write 4 minus R whole squared plus 3 minus square root of 5 whole squared equals R squared. This is the key equation, so let's simplify it carefully rather than rushing. First, consider 4 minus R whole squared. Using the identity a minus b whole squared equals a squared minus 2 multiplied by a multiplied by b plus b squared, we get 4 minus R whole squared equals 16 minus 8R plus R squared. Now, let's simplify the other square. 3 minus square root of 5 whole squared equals 3 squared minus 2 multiplied by 3 multiplied by square root of 5 plus square root of 5 squared. 3 squared is 9, square root of 5 squared is 5, and 2 multiplied by 3 multiplied by square root of 5 is 6 square root of 5. Therefore, 3 minus square root of 5 whole squared becomes 9 minus 6 square root of 5 plus 5. Combining the 9 and 5 gives 14, so we have 14 minus 6 square root of 5. Now substitute both expanded expressions into our Pythagorean equation. We get 16 minus 8R plus R squared plus 14 minus 6 square root of 5 equals R squared. Let's combine the ordinary numerical terms. 16 plus 14 gives 30. So we now have 30 minus 8R plus R squared minus 6 square root of 5 equals R squared. And here comes a very nice simplification. There is an R squared on both sides. We can subtract R squared from both sides, and those two R squared terms cancel completely. That leaves us with the 30 minus 6 square root of 5 minus 8R equals 0. Now, we want to isolate R. So let's move the term involving R to the other side. Adding 8R to both sides gives 30 minus 6 square root of 5 equals 8R. In other words, 8R equals 30 minus 6 square root of 5. Now divide both sides by 8. We get R equals 30 minus 6 square root of 5, all divided by 8. We can simplify this fraction by factoring 6 from the numerator. That gives us r equals 6 multiplied by the quantity 5 minus square root of 5 divided by 8. Now 6 over 8 can be reduced to 3 over 4. Therefore, the radius is r equals 3 multiplied by the quantity 5 minus square root of 5 divided by 4 units. Equivalently, we can distribute the 3 and write the exact answer as 15 minus 3 square root of 5, all divided by 4 units. That is our exact value. But let's also find a decimal approximation so we can understand the size of the radius. We know that square root of 5 is approximately 2.236. So 3 multiplied by square root of 5 is approximately 6.708. Then 15 minus 6.708 gives approximately 8.292. Dividing that by 4 gives approximately 2.073. So the radius is approximately 2.07 units. Notice how the entire solution came together from two main ideas. First, the tangent-secant theorem allowed us to determine the tangent length, RT, and then the Pythagorean theorem allowed us to determine the triangle dimensions, and finally, the radius. The key is not to treat these as isolated calculations. Each result gives us exactly the piece we need for the next step. We first found the entire hypotenuse PR as 5, then used the tangent-secant theorem to obtain RT as square root of 5, then used the original right triangle to find QR as 3, which gave us QT as 3 minus square root of 5. Finally, the perpendicular radius and the auxiliary perpendicular from O created a smaller right triangle, and the Pythagorean theorem produced the equation that allowed us to solve for the radius. So, our final answer is that the radius of the circle is 15 minus 3 square root of 5, all divided by 4 units, which is approximately 2.07 units. If this step-by-step explanation helped you see how the tangent-secant theorem and Pythagorean theorem work together in a geometry problem like this, take a moment to like the video, subscribe to the channel, and let me know in the comments whether you got the same radius.